Tonight, we're going to slow things down for a little while. Wherever you're listening from right now, whether it's late at night, early in the morning, or somewhere in between, I hope you can settle in comfortably. There's nothing you need to do, nothing you need to keep up with. Just listen quietly as we move through the universe together. Tonight's journey is about the life cycle of stars. How they form, how they change over billions of years, and how they eventually fade, collapse, or explode back into the cosmos. So take a moment to settle in. Maybe lower the lights a little, and let the night sky slowly unfold above you. Far beyond Earth, deep inside cold clouds of gas and dust, the next generation of stars is already beginning to form. For most of human history, the night sky appeared permanent. The stars seemed fixed, silent, unchanging. But stars are not permanent objects. They are born. They change slowly over immense periods of time, and eventually every star reaches an end. To understand the life cycle of stars, it helps to begin before stars even existed. Long before galaxies formed, long before planets existed, long before there was any light in the universe at all. Around 13.8 billion years ago, the universe began in an extremely hot and dense state. This event is known as the Big Bang. The Big Bang was not an explosion inside space. It was the rapid expansion of space itself. In the earliest moments, the universe was unimaginably hot. Temperatures were so high that ordinary matter could not exist in stable forms. There were no atoms, no stars, no planets, no light that could travel freely. The universe was filled with energy and tiny particles moving constantly through dense radiation. As space expanded, the universe slowly cooled. Cooling allowed particles to combine into simple forms of matter. Protons and neutrons formed first. Later, some of these particles joined together into the nuclei of the lightest elements. Most of the universe became hydrogen. A smaller portion became helium. Tiny traces of lithium also appeared. These simple elements would later become the raw material for every future star. But the universe still did not contain visible light in the way we experience it now. For hundreds of thousands of years, matter and radiation remained tightly connected. Light constantly collided with charged particles. Photons could not travel freely across space. The universe was opaque. Slowly, as cooling continued, electrons combined with atomic nuclei to form neutral atoms. This process is called recombination. Once neutral atoms formed, light could finally move through space without being scattered constantly. The universe became transparent. Some of that ancient light still exists today. It is known as the cosmic microwave background radiation, a faint glow left behind from the early universe. After this moment, the universe entered a very different period. There were still no stars, no galaxies, no visible structures. Space was mostly filled with enormous clouds of hydrogen and helium gas spread thinly across expanding darkness. This era is sometimes called the Cosmic Dark Ages. The darkness was not empty. Matter already existed everywhere, but there were no stars producing visible light. The universe was quiet, cold compared to its beginning, and incredibly vast. During this long period, gravity slowly began shaping the future. Gravity is the force that pulls matter together. Even tiny differences in density became important over enormous stretches of time. Some regions of space contained slightly more matter than others. These regions had slightly stronger gravity. Slowly, they attracted more gas toward themselves. Then more, and more. Over millions of years, the denser regions continued growing. The process was extremely slow. Human lifetimes are far too short to notice such changes directly. But across cosmic timescales, gravity is patient. It works continuously, quietly, without stopping. Gradually, giant structures began forming. Massive clouds of gas gathered together. Early galaxies started taking shape. Inside these growing regions, some pockets of gas became dense enough to collapse inward under their own gravity. These collapsing clouds would eventually create the first stars. The first stars in the universe were different from many stars we see today. The early universe contained almost no heavy elements. Elements like carbon, oxygen, silicon, and iron did not yet exist in meaningful amounts. Those elements had not been forged yet. They would only appear later inside stars themselves. So the earliest stars formed almost entirely from hydrogen and helium. Astronomers believe many of these first stars were extremely massive, much larger than our Sunday. Massive stars burn hotter and faster than smaller stars. Their lives are shorter, but they produce enormous amounts of energy. When the first stars ignited, the universe changed forever. Light returned to the cosmos. Ultraviolet radiation from these stars spread through space. It began interacting with surrounding hydrogen gas. Over time, this radiation reionized much of the universe. In simple terms, energetic light stripped electrons away from hydrogen atoms once again. This period is called the epoch of reionization. The first stars also began creating heavier elements through nuclear fusion. Deep inside stellar cores, hydrogen atoms fused together into helium. In larger stars, fusion continued creating heavier and heavier elements over time. Eventually, when some of these stars died, they scattered newly formed elements into space. Carbon, oxygen, nitrogen, iron. The ingredients required for planets and life slowly entered the universe. In many ways, stars transformed the cosmos from a simple place into a complex one. Before stars existed, the universe contained mostly basic gas. After stars appeared, chemistry became richer. Galaxies became brighter. New structures emerged. Stars became engines of cosmic evolution. Today, when we look into the night sky, we see only a small fraction of the stars that exist in the universe. Our own galaxy alone contains hundreds of billions of stars. Beyond the Milky Way are billions of other galaxies, many containing billions or even trillions of stars themselves. The observable universe is filled with stellar light. But despite how common stars appear now, every one of them began through the slow gathering of matter under gravity. Every star has a beginning, a long middle age, and an ending determined mostly by one thing: mass. Small stars can live for trillions of years, much longer than the current age of the universe. Massive stars may survive only a few million years before collapsing violently. The entire story of a star depends largely on how much matter it gathers at birth. Our own Sun formed around 4.6 billion years ago from a cloud of gas and dust enriched by older stars that died before it. The iron in Earth's core, the oxygen in the atmosphere, the carbon inside living things. All of these elements were forged in ancient stars long before the Earth existed. In a very literal sense, life on Earth is connected to stellar evolution. The universe is not static. It changes continuously. But the changes are usually slow beyond ordinary human experience. Galaxies drift. Stars form. Stars age. Stars die. And from their remains, new stars can eventually emerge again. The life cycle of stars is one of the great repeating patterns of the cosmos. A cycle shaped by gravity, energy, time, and matter. And although the universe can seem chaotic on small scales, the formation of stars follows physical laws that scientists can study and understand with remarkable precision. Modern telescopes allow astronomers to observe stellar nurseries inside distant nebulae. They can measure the temperatures of stars, their chemical composition, their mass, their age. By observing many stars at different stages, scientists have slowly reconstructed the story of stellar evolution across billions of years. Yet, even with modern science, stars still inspire a quiet sense of scale. Light from distant stars can take hundreds or thousands of years to reach Earth. Some stars visible in the night sky may no longer exist exactly as we see them now. Their light is simply still traveling across space. Looking at the cosmos is also a way of looking into the past. The deeper astronomers look into space, the farther back in time they can observe. Some telescopes now detect galaxies whose light began traveling toward us more than 13 billion years ago. These observations help scientists study the universe not long after the first stars appeared. And so the story of stars begins not with fire, but with darkness. A vast universe filled mostly with simple gas, slowly shaped by gravity across immense stretches of time. Eventually, those quiet clouds would gather into denser regions, cold regions hidden inside enormous cosmic structures, places where the first true stages of star formation could finally begin. In the depths of these giant molecular clouds, the universe would begin building stars from dust, gas, pressure, and gravity. After the first stars began illuminating the universe, vast regions of space still remained cold and dark. Between galaxies and within galaxies, enormous clouds of gas continued drifting slowly through space. These clouds would eventually become the birthplaces of future stars. A star does not appear suddenly. It begins as part of a much larger structure, a quiet region filled with gas, dust, and time. These regions are called molecular clouds. Molecular clouds are among the coldest places in the universe. Temperatures inside them can fall to around 10 degrees above absolute zero. At such low temperatures, atoms move slowly. This allows hydrogen atoms to bond together into hydrogen molecules. That is why they are called molecular clouds. These clouds are enormous beyond ordinary human imagination. Some stretch across dozens or even hundreds of light years. A single light year is the distance light travels in 1 year. roughly 9.5 trillion kilometers. Even the nearest stars are separated by immense distances. Molecular clouds are larger still. Despite their size, molecular clouds are extremely thin compared to Earth's atmosphere. The gas inside them is spread across vast volumes of space. If a human could somehow drift inside one without protective equipment, the cloud would still appear, almost like a vacuum. But over enormous scales, even sparse matter can eventually gather into something powerful. Most molecular clouds are made primarily of hydrogen gas. Helium is also abundant. Small amounts of heavier elements and microscopic dust grains are mixed throughout the cloud. These dust particles are important. They help block visible light. They cool the cloud, and they later contribute to the formation of planets and other structures. From far away, some molecular clouds appear beautiful and colorful in telescope images. Glowing reds, deep blues, soft purples. But these colors are usually assigned or enhanced to help scientists and viewers distinguish different gases and wavelengths. To the human eye alone, many nebulae would appear dim and ghostly. The word nebula is often used to describe giant clouds of gas and dust in space. Some nebulae are regions where stars are born. Others are remnants left behind after stars die. In the case of star formation, these regions are often called stellar nurseries. One of the most famous examples is located inside the Eagle Nebula, a structure known as the Pillars of Creation. Towering columns of gas and dust, slowly shaped by radiation and gravity. Inside those columns, new stars are forming gradually over long periods of time. Another well-known stellar nursery is the Orion Molecular Cloud Complex, located relatively close to Earth in astronomical terms, about 1,300 light-years away. The Orion Nebula inside this region contains many very young stars, some only a few 100,000 years old. Extremely young compared to our Sun, which is about 4.6 billion years old. Inside molecular clouds, gravity slowly works against another force: internal pressure. Gas naturally spreads outward over time. Gravity pulls inward. For long periods, these forces may remain roughly balanced. The cloud drifts quietly through space without forming stars immediately. But sometimes, the balance changes. A nearby supernova explosion may send shock waves through the cloud. Two clouds may collide gently, or gravity may simply amplify tiny density differences already present inside the cloud. Slowly, certain regions begin becoming denser than their surroundings. Once a region becomes dense enough, gravity strengthens further. More gas is pulled inward. The growing concentration attracts even more matter. A slow chain reaction begins. These denser regions are often called dense cores. They are the true seeds of future stars. A dense core may contain enough material to eventually form one star, or several stars together. Many stars are actually born in groups or clusters rather than alone. The collapse process is not fast. Gravity moves patiently. Over thousands and millions of years, gas continues drifting inward toward the center of the collapsing region. As the gas falls inward, gravitational energy converts into heat. The center slowly becomes warmer and denser. At first, the cloud remains dark in visible light. Thick dust blocks much of the light from escaping. But telescopes sensitive to infrared radiation can observe inside many of these hidden regions. Infrared light can pass through dust more effectively than visible light. This allows astronomers to study star formation occurring deep inside molecular clouds. Modern space telescopes have revealed extraordinary details inside these stellar nurseries. Streams of gas, young stars surrounded by disks, jets of material shooting outward into space. Regions that once appeared as dark patches are now understood as active environments where stars are constantly emerging. The gas inside molecular clouds is not perfectly still. Turbulence moves through the cloud slowly. Magnetic fields also influence how matter flows. Star formation is therefore complex. It involves gravity, pressure, radiation, turbulence, magnetic fields, and time interacting together. Even so, the basic pattern remains remarkably consistent throughout the universe. Cold gas gathers. Dense regions form. Gravity pulls matter inward. Heat slowly builds. Eventually, a new star begins taking shape. Not every part of a molecular cloud forms stars successfully. In fact, much of the gas may never become part of a star at all. Some material drifts away. Some is pushed outward by radiation from nearby young stars. Some remains dispersed through interstellar space. Star formation is surprisingly inefficient. Yet, across entire galaxies, enough gas collapses over time to create billions of stars. Some are small red dwarfs. Others become giant blue stars, many times larger than the Sunday. The initial amount of matter gathered during collapse will later determine much of the star's future life. Dense stellar nurseries can also become crowded environments. Young stars emit strong radiation and stellar winds. These winds are streams of charged particles flowing outward from stars into surrounding space. Radiation and winds can sculpt nearby clouds into pillars, arcs, and cavities. Over time, young stars may even disrupt the very cloud that formed them. In this way, stars reshape their environment almost immediately after birth begins. The surrounding cloud changes continuously. Gas disperses. New dense regions appear. More stars begin forming nearby. A stellar nursery is not static. It is an evolving ecosystem of gas, gravity, and energy. Some molecular clouds survive for millions of years before gradually dispersing. Others are torn apart more rapidly by nearby massive stars. Massive stars produce intense ultraviolet radiation capable of heating and ionizing surrounding gas. This energy can halt future star formation in some regions while triggering collapse in others. The universe often works through balance and feedback rather than simple linear processes. One generation of stars influences the next. Older stars enrich space with heavier elements. Young stars reshape their birth clouds. Exploding stars compress nearby gas. The cycle continues across cosmic time. Our own sun likely formed inside a stellar nursery, alongside many sibling stars billions of years ago. Most of those sibling stars have now drifted elsewhere through the Milky Way galaxy. The original molecular cloud that formed the sun no longer exists. It dispersed long ago. But traces of that ancient environment remain encoded in the chemical composition of the solar system itself. The dust within molecular clouds is especially important for planet formation later on. Tiny grains of carbon compounds, silicates, and ice eventually stick together through countless collisions. Over immense spans of time, those grains can become rocks, moons, and planets orbiting young stars. In that sense, planets begin forming even before a star is fully born. The calm appearance of the night sky hides an active and ongoing process. Across the Milky Way, new stars are forming even now, deep inside cold clouds invisible to the naked eye. Some of these stars may eventually host planetary systems. Some may possess worlds with oceans or atmospheres. Others may remain alone in darkness. Yet all stars begin in roughly the same way. A cold cloud, a slight imbalance, gravity pulling inward across unimaginable spans of time. Slowly, the dense center grows hotter and more compact. Matter continues falling inward. Pressure steadily increases. Eventually, the forming object reaches a critical stage. Deep within the collapsing core, temperature and density rise high enough for an entirely new phase to begin. The quiet cloud will soon produce a glowing young object known as a protostar. Deep inside a collapsing molecular cloud, gravity continues pulling matter inward. Gas drifts slowly toward the densest region. Dust follows with it. Over time, the center becomes warmer, denser, and more compact. This marks the beginning of a protostar. A protostar is not yet a true star. Nuclear fusion has not fully begun in its core. But the object is no longer just a cold cloud either. It is a forming star. The word protostar simply means an early stage of stellar development, a star in the process of becoming stable. This stage can last for hundreds of thousands or even millions of years, depending on the mass of the object. As material falls inward, gravitational potential energy converts into heat. The center grows increasingly hot. Pressure rises steadily. Unlike mature stars, however, the energy source of a protostar mainly comes from gravitational collapse itself, rather than sustained nuclear fusion. In many ways, a protostar is still assembling. Matter from the surrounding cloud continues feeding into it. Gas spirals inward gradually. The young object gains mass over time. The collapsing cloud also begins rotating faster as it contracts. This happens because angular momentum is conserved. The same physical principle can be observed when an ice skater pulls their arms inward and spins faster. As the cloud shrinks, rotation speeds up. Because of this rotation, the infalling material does not collapse directly into the center all at once. Instead, much of the gas forms a flattened, rotating structure around the protostar. This structure is called a protoplanetary disk. These disks are extremely important. They contain the material that may later form planets, moons, asteroids, and comets. Around many young stars, the formation of planetary systems begins almost immediately alongside stellar birth. Our own solar system likely formed from such a disk around the young sun billions of years ago. Tiny dust particles collided repeatedly. Some stuck together. Gradually, larger bodies formed over immense spans of time. But during the protostar stage, the central object itself still dominates the environment. The core continues becoming hotter as gravity compresses it further. temperatures can rise to several thousand degrees Celsius. The protostar begins glowing, often mostly in infrared wavelengths. Thick dust surrounding the young object still blocks much visible light from escaping directly. To ordinary human eyes, many protostars would remain hidden inside dark clouds. But infrared telescopes can detect the heat radiating from these forming stars. Modern observatories have captured images of hundreds of protostars scattered throughout nearby stellar nurseries. Some protostars form alone. Others form in pairs or larger groups. Binary star systems are actually very common throughout the galaxy. In some cases, two protostars form together from the same collapsing region and continue orbiting each other for billions of years afterward. The protostar phase can be turbulent. Matter does not always fall inward smoothly. Magnetic fields interact with charged particles inside the disk and surrounding gas. These interactions can generate powerful jets shooting outward from the poles of the protostar. These jets are known as bipolar outflows, streams of gas accelerated into space at high speeds. They can extend for light years beyond the forming star itself. Astronomers often observe glowing regions where these jets collide with surrounding gas clouds. The exact mechanisms behind these jets are complex and still actively studied. But magnetic fields clearly play a major role in channeling matter outward. In a sense, the forming star both gathers material inward and ejects some material back outward into space at the same time. The surrounding environment, therefore, remains dynamic and constantly changing. Gas flows inward through the disk. Radiation escapes outward. Jets carve through nearby clouds. The young stellar system slowly evolves towards stability. As more mass accumulates in the center, pressure and temperature continue rising deeper inside the protostar. The core becomes denser than almost anything humans experience naturally on Earth. Atoms are squeezed tightly together by gravity. Eventually, temperatures inside the core approach several million degrees Celsius. At these extraordinary temperatures, atomic nuclei begin moving fast enough to overcome their natural electrical repulsion. This allows hydrogen nuclei to fuse together. Fusion is the process that powers stars. During hydrogen fusion, small amounts of mass convert into energy. This follows Einstein's famous relationship between mass and energy. Even tiny amounts of mass can produce enormous amounts of energy. However, in a protostar, sustained hydrogen fusion has not fully stabilized yet. Small fusion reactions may briefly occur in some cases, especially involving deuterium, which is a heavier form of hydrogen. But the star has not yet reached long-term equilibrium. A true star exists in hydrostatic equilibrium. Gravity pulls inward. Pressure from fusion pushes outward. These forces balance one another. During the protostar phase, gravity still dominates the process overall. Collapse continues gradually. The object remains unstable compared to a mature star. Yet each passing year brings the core closer to the conditions required for stable fusion. The future of the protostar depends mainly on one thing: mass. If enough matter accumulates, temperatures and pressures eventually become sufficient for long-term hydrogen fusion. The object officially becomes a main sequence star. But if the protostar lacks sufficient mass, a different outcome occurs. Some collapsing objects never become true stars at all. If the mass remains below roughly 8% of the Sun's mass, the core never grows hot enough to sustain ordinary hydrogen fusion. These objects are known as brown dwarfs. Brown dwarfs are sometimes called failed stars, though the phrase can be misleading. They are real astronomical objects with their own unique properties. Larger than most planets. Smaller than true stars. Some can briefly fuse deuterium, but not regular hydrogen efficiently over long periods. This means not every collapsing cloud successfully creates a full star. The outcome depends delicately on how much material gravity gathers together during formation. Inside large stellar nurseries, many protostars may exist simultaneously. Some become red dwarfs. Some become stars similar to the Sunday. A few may grow into massive blue giants. Their futures diverge dramatically based on their birth mass. Yet at this early stage, they all share certain similarities. They are still hidden inside dusty clouds, still gathering matter, still changing slowly under gravity's influence. The timescales involved remain immense by human standards. Even relatively fast star formation requires many thousands or millions of years. Entire civilizations could rise and disappear on Earth while a distant protostar continues quietly evolving inside a molecular cloud. Eventually, as surrounding gas disperses, the young object becomes more visible. Radiation from the forming star pushes away nearby material. Stellar winds help clear the surrounding region. The once hidden object slowly emerges from its dusty cocoon. At the same time, the core continues heating toward a critical threshold. Around 10 million degrees Celsius, sustained hydrogen fusion becomes possible in earnest. Once this happens, the balance of forces changes fundamentally. Energy from fusion creates outward pressure strong enough to counteract gravity continuously. Collapse slows dramatically. Stability emerges for the first time. The protostar transitions into the longest and most stable phase of stellar life. A true star is born. It enters what astronomers call the main sequence. Here, for millions or billions of years, the star will shine steadily through the darkness of space. A star reaches the main sequence when gravity and pressure finally come into balance. Inward gravitational collapse no longer dominates completely. Outward pressure, generated by nuclear fusion, now pushes back continuously from the core. The star becomes stable for the first time in its existence. This balance is known as hydrostatic equilibrium. Gravity constantly pulls matter inward. Fusion constantly pushes outward. As long as these forces remain balanced, the star can shine steadily for immense periods of time. The main sequence is the longest phase in the life of most stars. A star may spend around 90% of its entire lifetime in this stage. During this time, hydrogen fusion powers the core continuously. Deep inside the core, temperatures remain extraordinarily high, millions of degrees Celsius. Matter exists in a state called plasma. In plasma, electrons are no longer bound tightly to atomic nuclei. The extreme heat prevents ordinary atomic structures from remaining stable. Under these conditions, hydrogen nuclei move rapidly enough to overcome their electrical repulsion. They collide and fuse together. In stars like the Sun, the dominant process is called the proton-proton chain, Through several steps, hydrogen nuclei combine to form helium. Tiny amounts of mass disappear during the process. That missing mass becomes energy. The energy eventually travels outward from the core and escapes into space as radiation and light. This process allows stars to shine continuously for millions or billions of years. Every second, the Sun converts around 600 million tons of hydrogen into helium. Yet the Sun contains so much hydrogen that it can continue this process for roughly 10 billion years in total. Our Sun is currently about halfway through its main sequence lifetime. It formed around 4.6 billion years ago. It will likely remain stable for roughly another 5 billion years before major changes begin. The Sun is considered an average-sized star, not especially large, not especially small. Throughout the universe, stars exist across a huge range of masses and temperatures. Some stars contain only a fraction of the Sun's mass. Others may contain tens or even hundreds of times more mass. Mass is the single most important factor determining how a star evolves. More massive stars possess stronger gravity. Stronger gravity compresses the core more intensely. This increases temperature and pressure. Fusion then proceeds much faster. Smaller stars burn fuel slowly and calmly. Massive stars burn fuel rapidly and violently by comparison. This creates one of the great paradoxes of stellar evolution. Larger stars contain more fuel, but they consume it far more quickly. As a result, massive stars usually live much shorter lives than smaller stars. A very massive star may survive only a few million years. Smaller red dwarf stars may survive for trillions of years. In fact, the universe is not yet old enough for any red dwarf star to have completed its full life cycle naturally. The color of a star also depends mainly on temperature. Cooler stars appear red or orange. Hotter stars appear white or blue. The Sun appears yellowish from Earth's surface, partly because of Earth's atmosphere scattering shorter wavelengths of light. From space, sunlight appears closer to white. Astronomers classify stars into spectral types based on temperature. The main sequence includes cool red stars, hotter yellow stars like the Sun, and extremely hot blue stars. Surface temperatures can range from under 3,000 degrees Celsius to over 40,000 degrees Celsius. Despite these differences, all main sequence stars share the same essential balance: gravity pulling inward, fusion pushing outward. A stable engine of energy generation sustained over immense spans of time. Inside a star, energy does not escape instantly from the core. The process is surprisingly slow. Photons generated near the center may take thousands or even hundreds of thousands of years to reach the surface. Inside the star, photons constantly interact with particles. They are absorbed and re-emitted countless times. Their path outward resembles a slow, random walk more than a direct journey. Eventually, the energy reaches the outer layers and radiates into space. Some stars transport energy differently depending on their structure. In certain layers, energy moves mainly through radiation. In others, hot plasma physically rises and cooler plasma sinks in a process called convection. The Sun's outer layers contain large convection zones constantly in motion. These motions contribute to magnetic activity, sunspots, solar flares, coronal mass ejections, Although the Sun appears calm from Earth most of the time, it is actually a dynamic and active star. Even so, compared to many stars, the Sun is relatively stable. Some stars vary greatly in brightness. Others rotate extremely rapidly. Some possess magnetic fields vastly stronger than the Sun's. The universe contains remarkable diversity, even among stars occupying the same general phase of life. Main sequence stars also influence their surrounding environments continuously. Radiation flows outward into space. Stellar winds carry streams of charged particles away from the star. These winds interact with nearby planets, dust, and interstellar gas. Earth itself exists inside the Sun's extended atmosphere in a sense. The solar wind reaches far beyond the planets. Earth's magnetic field helps protect the atmosphere from much of this radiation and charged particle flow. Without the Sun, life on Earth would not exist. Nearly all biological energy on Earth ultimately comes from sunlight, either directly or indirectly. Plants convert solar energy into chemical energy through photosynthesis. Ecosystems then build upon that foundation. The Sun also shapes Earth's climate, weather, and daily cycles of light and darkness. Yet the Sun is only one ordinary star among hundreds of billions inside the Milky Way galaxy. Countless other planetary systems likely orbit distant stars across the universe. Many exoplanets discovered by astronomers orbit main sequence stars. Some lie within regions where liquid water could potentially exist under suitable atmospheric conditions. Scientists often focus attention on stable main sequence stars when searching for environments that may support life. Stability matters greatly for planetary systems. A star that changes brightness violently or dies quickly may not provide enough time for complex life to emerge on nearby planets. Smaller and longer-lived stars may offer far more time for biological evolution. Red dwarf stars are especially interesting in this regard. They are the most common type of star in the Milky Way. Smaller and cooler than the Sunday, extremely long-lived. Some theoretical calculations suggest certain red dwarfs may survive for trillions of years. By comparison, massive blue stars live brief and energetic lives. They produce tremendous amounts of ultraviolet radiation. Their luminosity can exceed the Sun's by hundreds of thousands or even millions of times. Yet, they exhaust their fuel quickly and die young. During the main sequence phase, however, even massive stars achieve temporary stability. Their cores continue converting hydrogen into helium steadily. The balance remains intact. For long periods, the star appears almost unchanging from a human perspective. Ancient civilizations observed many of the same stars still visible today. Human history passes quickly compared to stellar evolution. Entire empires rise and disappear while stars continue their slow nuclear burning across cosmic time. Yet the balance inside a main sequence star is not permanent forever. Hydrogen fuel in the core gradually decreases. Helium ash accumulates slowly over billions of years. Eventually, the core composition changes enough that the delicate equilibrium begins shifting again. The future transformation depends heavily on mass. Small stars evolve slowly and gently. Massive stars undergo far more dramatic changes. But all main sequence stars ultimately face the same fundamental problem. The hydrogen fuel powering the core is finite. No star can remain in perfect balance forever. Over immense stretches of time, even the most stable stars begin changing quietly from within. Deep in the core, the long process of aging has already begun. Not all stars live the same kind of life. Some burn slowly and steadily for trillions of years. Others race through their existence in only a few million years. The difference comes mainly from mass. Mass determines how strongly gravity compresses a star's core. Stronger gravity produces higher temperatures and pressures. Higher temperatures increase the rate of nuclear fusion. And faster fusion means fuel is consumed more rapidly. This creates an unusual pattern in stellar evolution. The largest stars possess the greatest supply of hydrogen fuel. Yet, they burn through that fuel at extraordinary speeds. Massive stars therefore live much shorter lives than small stars. A small red dwarf star may survive for trillions of years. A star much larger than the Sun may live only a few million years before dying. In cosmic terms, some massive stars are born and die almost instantly. The relationship between mass and brightness is not linear. A star twice as massive as the Sun is not merely twice as bright. It may be many times brighter. Extremely massive stars can outshine the Sun by hundreds of thousands or even millions of times. To produce such immense energy, fusion inside the core must proceed at tremendous rates. The star effectively spends its fuel recklessly. Massive stars are sometimes compared to engines running at maximum power continuously. Smaller stars behave differently. Their weaker gravity creates lower core temperatures. Fusion occurs more slowly. Energy output remains modest. They conserve fuel carefully across immense spans of time. Red dwarf stars are the clearest example of this slow and efficient behavior. These stars are small, cool, and dim compared to the Sunday. Yet they are remarkably stable. Because they burn hydrogen slowly, their lifetimes become extraordinarily long. Many red dwarfs also mix their internal material more completely than larger stars. This means fresh hydrogen can continue reaching the core over time. They use a larger fraction of their available fuel instead of leaving much of it unused. The universe itself is only about 13.8 billion years old. That sounds ancient from a human perspective. Yet many red dwarfs are expected to survive far longer than this current cosmic age. None have existed long enough to naturally complete their full stellar evolution yet. The opposite extreme can be found among blue giant and blue supergiant stars. These stars are extremely hot, extremely luminous, and extremely short-lived. Their surface temperatures can exceed tens of thousands of degrees Celsius. They emit intense ultraviolet radiation into surrounding space. Blue stars appear blue because hotter objects radiate more strongly at shorter wavelengths of light. Cooler stars shift toward orange and red wavelengths instead. The color of a star therefore provides astronomers with important information about temperature. Massive stars also shape their surroundings dramatically. Their radiation ionizes nearby gas clouds. Their stellar winds push material outward into space. In crowded stellar nurseries, massive stars can influence the formation of neighboring stars and planets. Some massive stars produce winds so strong that they lose large amounts of mass throughout their lives. Streams of charged particles flow outward continuously at high speeds. Over time, these winds can sculpt surrounding nebulae into vast, glowing structures. One famous example of a massive star is Betelgeuse, a red supergiant located in the constellation Orion. Betelgeuse is much larger than the Sunday. If placed at the center of our solar system, its outer layers would extend beyond the orbit of Mars and possibly even Jupiter, depending on how its atmosphere is measured. Yet despite its enormous size, Betelgeuse is nearing the end of its life already. Astronomers estimate it is only around 10 million years old. The Sun, by comparison, is over 4 billion years old and still comfortably middle-aged. Massive stars live quickly because their cores become incredibly hot and dense. Fusion rates increase dramatically under such conditions. In stars more massive than the Sun, another fusion mechanism called the CNO cycle often dominates hydrogen fusion. The CNO cycle uses carbon, nitrogen, and oxygen as catalysts during the fusion process. It becomes much more efficient at high temperatures than the proton-proton chain used mainly by stars like the Sunday. This allows massive stars to generate huge amounts of energy rapidly. The intense energy production creates enormous outward pressure. This pressure balances gravity temporarily, but the balance is expensive in terms of fuel consumption. Massive stars sacrifice longevity for power. In many ways, stars resemble candles burning at different intensities. A small flame may last through the night. A giant flame burns brilliantly but disappears quickly. The same principle appears throughout stellar evolution. The environments around massive stars are often hostile to life as humans understand it. Strong ultraviolet radiation can strip atmospheres from nearby planets. Violent stellar winds continuously bombard surrounding space. And the short lifetimes of massive stars may not allow enough time for complex biological evolution on nearby worlds. Smaller stars may provide more stable conditions over longer periods. This is one reason astronomers are interested in planets orbiting relatively calm and long-lived stars. Time is an important ingredient for planetary evolution and potentially for life. Yet massive stars play another critical role in the universe. They create many of the heavy elements necessary for planets and biology in the first place. Without generations of massive stars living and dying before the Sun formed, Earth would not possess elements like oxygen, carbon, silicon, or iron in such abundance. Massive stars therefore contribute both destruction and creation. Their short lives enrich galaxies chemically. Their deaths scatter new elements into interstellar space. Future stars and planets later form from that enriched material. Meanwhile, smaller stars preserve energy slowly across unimaginable spans of time. Some future eras of the universe may belong almost entirely to red dwarfs after larger stars have already vanished. Far trillions of years from now, tiny stars may continue glowing quietly long after the brightest giants disappeared. From Earth, however, massive stars often dominate human attention because they are so luminous. Bright blue stars stand out dramatically in the night sky. Their intense light travels across great distances. Some of the most recognizable stars visible to the naked eye are massive stars nearing the ends of their lives already. Stellar clusters reveal this pattern clearly. Young star clusters often contain bright blue stars because massive stars are still alive there. Older clusters lack these stars because they already died long ago. Astronomers use such observations to estimate the ages of stellar populations. The mass of a star also influences how it eventually dies. Small stars experience relatively gentle endings. Massive stars often end in catastrophic explosions called supernovae. Their extreme beginnings foreshadow extreme conclusions. Yet, regardless of size, all stars spend much of their existence quietly balancing gravity against fusion. The night sky appears peaceful because these changes unfold over timescales far beyond ordinary human experience. A star that seems unchanged across generations may actually be aging continuously deep within its core. Even now, inside the Sun, hydrogen slowly becomes helium, second by second. Over billions of years, this gradual change alters the internal structure of the star. For massive stars, the same process happens far faster. Their fuel disappears rapidly. Their cores evolve quickly. And eventually, stability begins to weaken. The long middle age of stellar life cannot last forever. As hydrogen becomes depleted inside the core, the next great transformation quietly approaches. For billions of years, a sun-like star remains relatively stable. Hydrogen fuses into helium deep inside the core. Gravity and pressure remain balanced. From a distance, the star appears calm and unchanging. But inside the core, slow changes continue accumulating over immense spans of time. Hydrogen fuel gradually decreases. Helium slowly builds up. Eventually, the balance that sustained the star for so long begins shifting. In stars similar to the Sun, hydrogen fusion occurs mainly in the core during the main sequence phase. As fusion continues, the amount of hydrogen available in the center steadily shrinks. The core becomes increasingly dominated by helium. Helium behaves differently from hydrogen under these conditions. The temperatures inside the aging core are not yet high enough for helium fusion to begin immediately. As a result, the helium core no longer produces enough outward pressure through fusion. Gravity begins compressing the core inward once again. The core contracts slowly. Pressure and temperature rise further. At the same time, hydrogen fusion continues in a shell surrounding the helium core rather than directly inside it. This shell fusion actually generates more energy than before. The outer layers of the star respond dramatically to the increased energy output. They begin expanding outward into space. The star enters the red giant phase. During this transformation, the star grows enormously in size. Its outer atmosphere expands far beyond its original dimensions. Although the surface becomes cooler than before, the much larger size causes the star to shine very brightly overall. Cooler surfaces emit redder light. This is why giant aging stars often appear orange or red. The term red giant refers both to their enormous size and their cooler surface temperature compared to hotter blue or white stars. The future Sun will eventually become a red giant several billion years from now. As it expands, conditions throughout the solar system will change profoundly. Mercury will almost certainly be engulfed by the expanding Sunday. Venus will likely be engulfed as well. The fate of Earth is less certain in detail, but the planet will become uninhabitable long before that stage. As the Sun brightens gradually over time, Earth's oceans would eventually evaporate. Surface temperatures would rise dramatically. The atmosphere would change irreversibly. These transformations would occur over immense spans of time, not suddenly. The red giant phase itself can last hundreds of millions to over a billion years, depending on the star's mass. Even though it represents an aging stage, it still unfolds slowly on human timescales. The expanding outer layers become more diffuse and loosely bound by gravity. Inside the contracting core, temperatures continue rising steadily. Eventually, the core reaches around 100 million degrees Celsius. Under these extreme conditions, helium fusion finally becomes possible. Helium nuclei fuse together to form heavier elements, mainly carbon and oxygen. This process is sometimes called the triple alpha process because it involves helium nuclei, also known as alpha particles. In stars roughly similar to the Sun, helium fusion can begin rather suddenly in an event called the helium flash. Despite the dramatic name, this event occurs deep inside the core and is not directly visible externally as an explosion. It is caused by the unusual physical conditions inside the compressed helium core. Once helium fusion stabilizes, the star temporarily reaches a new equilibrium. The core stops contracting so rapidly. The outer layers may shrink somewhat compared to the peak of the red giant phase. For a time, the star again maintains relative stability. But this phase is shorter than the original main sequence stage. Helium fuel is far less abundant than hydrogen, and helium fusion is less efficient energetically. The later stages of stellar evolution, therefore, proceed more quickly. Eventually, helium in the core also becomes depleted. Carbon and oxygen accumulate. For stars around the Sun's mass, the core never becomes hot enough to fuse carbon efficiently. The star has reached a major limit in its evolution. Gravity begins dominating again within the inert carbon-oxygen core. Meanwhile, fusion continues temporarily in surrounding shells of hydrogen and helium. The outer layers become increasingly unstable. Pulsations and stellar winds strengthen. The star begins losing mass into surrounding space. Huge amounts of gas drift outward slowly over time. These escaping outer layers can create beautiful glowing structures known as planetary nebulae. The name is somewhat misleading. Planetary nebulae have nothing to do with planets directly. Early astronomers gave them this name because some appeared vaguely planet-like through small telescopes. In reality, a planetary nebula is the exposed outer atmosphere of an aging star illuminated by the hot stellar core left behind. Expanding shells of gas drift through interstellar space at relatively moderate speeds. Over time, these gases mix back into the galaxy. This process enriches interstellar space with heavier elements created during the star's lifetime. Carbon atoms formed deep inside stars eventually become part of future clouds, planets, and perhaps living organisms. Stellar evolution is also a process of chemical recycling across the cosmos. During the red giant stage, the internal structure of the star becomes layered. Different fusion processes may occur in shells surrounding the core. The star becomes more complex internally than during its simpler main sequence years. Yet from far away, the changes still appear slow and peaceful. A distant observer watching over only a human lifetime would notice little change. The dramatic transformations of stellar aging occur across spans of time difficult for humans to intuitively grasp. the Sun itself still has billions of stable years remaining. Humanity exists relatively early in the Sun's overall lifespan. The sunlight warming Earth today comes from a star still comfortably within its long middle age. Yet even now, the Sun changes gradually. Main sequence stars slowly brighten over time as helium accumulates in their cores. The Sun today is somewhat brighter than it was billions of years ago when Earth first formed. These subtle long-term changes influence planetary climates and environments. Stellar evolution and planetary evolution are deeply connected processes. The future habitability of planets depends strongly on the changing energy output of their stars. Smaller stars evolve more slowly than the Sunday. Larger stars evolve much faster. But for Sun-like stars, the red giant stage represents the transition from stable adulthood into stellar old age. The once balanced core gradually transforms into something denser and stranger. The outer layers drift away into space. The star sheds much of its former self. What remains afterward is no longer a giant star at all. Beneath the expanding nebula, the exposed stellar core continues glowing intensely with residual heat. Small in size, extremely dense, slowly cooling across billions of years. The long life of a Sun-like star quietly approaches its final stage. After a Sun-like star sheds its outer layers, the remaining core becomes exposed to space. The giant red atmosphere drifts outward slowly, forming a glowing planetary nebula. At the center, something much smaller remains behind. A white dwarf. A white dwarf is not an ordinary star anymore. Nuclear fusion has effectively ended in its core. It no longer generates large amounts of new energy through fusion reactions. Instead, it shines mainly because of leftover heat from its earlier life. White dwarfs are among the densest objects in the universe. A typical white dwarf may contain a mass similar to the Sun compressed into a volume roughly comparable to Earth. The density becomes extraordinary. A teaspoon of white dwarf matter would weigh many tons under Earth's gravity. The matter inside no longer behaves like ordinary gas or plasma in the usual sense. Quantum physics becomes critically important. In an ordinary star, thermal pressure from hot gas helps resist gravity. But inside a white dwarf, another form of pressure dominates: electron degeneracy pressure. This pressure arises from the principles of quantum mechanics. Electrons cannot all occupy identical quantum states simultaneously. When matter becomes compressed enough, this creates a powerful resistance against further compression. The white dwarf therefore remains stable even without ongoing fusion. Gravity continues pulling inward constantly. Degeneracy pressure pushes back. Another equilibrium forms, though very different from the balance inside a normal main sequence star. Most white dwarfs are composed mainly of carbon and oxygen left behind from the earlier fusion stages of the star. Some lower-mass white dwarfs may contain more helium. More massive stellar remnants can contain heavier elements in certain cases. But carbon and oxygen are especially common outcomes for Sun-like stars. When a white dwarf first forms, it remains extremely hot. Surface temperatures can exceed 100,000 degrees Celsius initially. Over time, however, the white dwarf slowly radiates heat away into space. Unlike active stars, No large-scale fusion replenishes the lost energy. Cooling therefore continues gradually across billions and trillions of years. The white dwarf slowly dims. Even though white dwarfs are small, they can remain visible for immense periods because they begin so hot. Their cooling process is extremely slow. Many white dwarfs observed today formed billions of years ago and are still glowing faintly. Astronomers often use white dwarfs to estimate the ages of stellar populations. Because white dwarfs cool predictably over time, their temperatures provide clues about how long they have existed. In a sense, they function as cosmic clocks. The eventual fate of a white dwarf is thought to be a black dwarf, a cold stellar remnant that has radiated away nearly all remaining heat. However, the universe is not yet old enough for any true black dwarfs to exist naturally. Even the oldest white dwarfs formed after the universe began only 13.8 billion years ago. Cooling completely into black dwarfs likely requires far longer spans of time, possibly trillions of years or more. White dwarfs, therefore, represent a glimpse into the distant future of the cosmos. Long after many bright stars disappear, countless cooling white dwarfs may still drift quietly through galaxies. The formation of a white dwarf also reveals an important limit in stellar evolution. Stars similar to the Sun never develop cores hot enough to fuse carbon efficiently. Their evolution stops at carbon and oxygen remnants. More massive stars follow very different paths later on. There is also an important mass limit for white dwarfs themselves. It is known as the Chandrasekhar limit, roughly 1.4 times the mass of the Sunday. If a white dwarf exceeds this limit, electron degeneracy pressure can no longer support it fully against gravity. Under ordinary isolated conditions, most white dwarfs remain safely below this threshold. But in certain binary star systems, mass transfer can push a white dwarf toward instability. In some cases, this leads to a thermonuclear explosion known as a Type Ia supernova. These explosions are extraordinarily bright and important in astronomy because they help scientists measure vast cosmic distances. But isolated white dwarfs generally cool peacefully over time instead. White dwarfs possess intense gravity at their surfaces. Although small in size, their compact mass creates strong gravitational fields. A human standing on the surface of a white dwarf would experience gravity hundreds of thousands of times stronger than Earth's gravity. Yet despite these extreme conditions, white dwarfs are relatively quiet compared to many other stellar remnants. No giant explosions occur continuously. No powerful fusion reactions dominate their interiors anymore. They are slowly fading embers of former stars. The planetary nebula surrounding a young white dwarf also changes gradually over time. At first, ultraviolet radiation from the hot white dwarf causes the expanding gas shells to glow brightly. Beautiful patterns appear in telescope images. Rings, filaments, symmetrical bubbles. These structures are shaped by stellar winds, magnetic fields, and interactions between different layers of escaping gas. No two planetary nebulae appear exactly alike. Yet all are temporary. Over tens of thousands of years, the nebula disperses gradually into interstellar space. The glowing gases thin out and fade. Eventually, only the white dwarf remains clearly visible. the surrounding material becomes part of the galaxy once more. Some of that dispersed matter may later join future molecular clouds, future stars, future planets, future living systems, perhaps. Stellar evolution continually recycles matter throughout the cosmos. The carbon in Earth's biology likely passed through ancient stars similar to the Sun long before the solar system existed. The oxygen humans breathe was forged inside earlier generations of stars. White dwarfs, therefore, represent not merely endings, but part of a larger cosmic cycle. Many stars throughout the Milky Way will eventually become white dwarfs. Red dwarfs may follow different, slower evolutionary paths. Massive stars experience far more violent endings. But Sun-like stars conclude their lives in relatively gentle ways. Their outer layers drift outward quietly. Their cores shrink into dense stellar remnants. Their remaining heat fades slowly through the darkness of space. A long cooling process begins. From far away, a white dwarf may appear small and faint compared to giant luminous stars. Yet it represents one of the final stable products of stellar evolution. Matter compressed into extraordinary density, held stable not by ordinary gas pressure, but by the strange rules of quantum mechanics. The future universe may eventually become populated largely by such remnants. Cooling white dwarfs drifting through increasingly dark galaxies after the brightest stars have already vanished. But not all stars end so quietly. Stars much more massive than the Sun follow a far more dramatic path as they age. Their immense mass allows fusion to continue far beyond carbon and oxygen. Their cores grow hotter and denser still. And their final stages become increasingly unstable as they approach catastrophic collapse. Massive stars live very different lives from stars like the Sunday. Their enormous mass creates tremendous pressure deep inside their cores. Temperatures rise far higher than in smaller stars. Fusion reactions proceed rapidly and intensely. These stars shine with extraordinary brightness throughout their relatively short lives. But their final stages become increasingly unstable and complex. After exhausting hydrogen in their cores, massive stars do not stop at helium fusion. Their gravity is strong enough to continue compressing the core to even higher temperatures. Helium begins fusing into carbon and oxygen. Later, carbon fusion becomes possible. Then, neon, oxygen, silicon. One fusion stage follows another deep inside the star. This creates a layered internal structure, sometimes compared to an onion. Different elements fuse in different shells surrounding the core. Hydrogen fusion may continue in outer layers, while heavier elements fuse closer to the center. Each stage of fusion produces energy for a shorter period than the one before it. Hydrogen burning may last millions of years. Helium burning lasts less time. Carbon burning proceeds faster still. In the final stages, silicon fusion may last only days before collapse begins. Massive stars therefore age increasingly rapidly near the ends of their lives. Their interiors become unstable and dynamic. Radiation pressure, gravity, and fusion compete continuously inside the core. The balance becomes more fragile over time. As massive stars evolve, many expand into enormous red supergiants. These are among the largest stars in the observable universe by volume. Their outer atmospheres swell outward across immense distances. Betelgeuse is one famous example. Located in the constellation Orion, visible to the naked eye from Earth. Betelgeuse is estimated to be hundreds of times larger than the Sun in radius. Despite their enormous size, red supergiants often have relatively cool surfaces compared to smaller blue stars. Their outer atmospheres become diffuse and expanded. Surface temperatures may fall to only a few thousand degrees Celsius. This cooler temperature gives them their reddish appearance. Yet beneath those cool outer layers, the cores remain unimaginably hot and active. Multiple fusion reactions occur simultaneously in different regions. The star becomes internally layered and increasingly complex. Massive stars also lose huge amounts of material through stellar winds during these stages. Their powerful radiation pushes gas outward continuously into surrounding space. Some stars lose several Earth masses of material over relatively short astronomical periods. The gas escaping from these stars enriches nearby interstellar space with heavy elements created through fusion. Carbon, oxygen, neon, magnesium. The chemical complexity of galaxies increases generation after generation because of these stellar processes. During the red supergiant phase, the star's outer atmosphere may pulsate irregularly. Convection currents move enormous volumes of gas slowly through the outer layers. Some convection cells on red supergiants may be larger than Earth's entire orbit around the Sunday. The surfaces of these stars are therefore not smooth or stable. They shift continuously over time. Bright regions emerge and fade. Gas rises and falls. The star resembles a giant, unstable ocean of plasma. Massive stars also rotate at different speeds depending on their history and mass. Rotation influences how material mixes inside the star. Magnetic fields may become extremely powerful. These factors affect how the star evolves and eventually dies. Yet despite all this activity, the star may still appear peaceful from great distances. Human lives pass too quickly to notice most stellar changes directly. Even dramatic stellar evolution unfolds slowly on ordinary timescales. The universe hides enormous transformations behind immense patience. Deep within the core, fusion reactions continue building heavier elements step by step. But this process cannot continue forever. Fusion only releases energy efficiently up to a certain point. Iron marks a critical boundary in stellar physics. Fusing lighter elements into heavier ones usually releases energy. But iron behaves differently. Fusion involving iron consumes energy instead of releasing it. Once a massive star develops a large iron core, the situation becomes unstable. The core can no longer generate enough fusion energy to support itself against gravity. A crisis begins deep inside the star. Gravity suddenly gains the advantage. The iron core starts collapsing inward extremely rapidly. The collapse can occur in less than a second. Conditions become extraordinary. Temperatures rise into the billions of degrees. Atomic nuclei break apart. Electrons and protons combine into neutrons. The core compresses with terrifying intensity. Yet from the star's surface, the final collapse may not be obvious immediately. The enormous outer layers still surround the collapsing center. For a brief moment, the giant star continues existing outwardly while catastrophe unfolds within. A silent imbalance spreads through the star's interior. Massive stars, therefore, spend much of their lives balancing on the edge of instability. Their immense energy production sustains them temporarily. But the very mass that powers their brilliance ultimately seals their fate. They evolve too quickly and too intensely to end gently. The contrast with stars like the Sun is profound. Sun-like stars cool into white dwarfs quietly. Massive stars continue fusing heavier elements until collapse becomes unavoidable. Their endings reshape entire regions of galaxies. Before the final collapse occurs, red supergiants represent one of the most visually striking stages in stellar evolution. Giant swollen atmospheres glowing red against the darkness of space. Vast shells of gas slowly drifting outward. Internally unstable. Externally majestic. Some red supergiants are so large that if placed at the center of our solar system, their outer layers would extend beyond the orbit of Jupiter. Yet their matter remains incredibly diffuse in the outer regions. A spacecraft passing through those outer layers might not even experience them as a solid surface at all. Massive stars also tend to form in active regions alongside many other stars. Their ultraviolet radiation illuminates nearby gas clouds. Their stellar winds carve cavities into surrounding nebulae. They dominate the appearance and evolution of their local environments. Although rare compared to smaller stars, massive stars play an outsized role in galactic evolution. They manufacture heavy elements rapidly. They energize surrounding space. And their deaths distribute newly forged material across enormous distances. The future Earth itself depends on elements produced by ancient massive stars long ago. Every atom of calcium in human bones, every atom of oxygen in Earth's atmosphere, every atom of iron in Earth's core. All were forged through earlier generations of stellar evolution. Inside the aging red supergiant, however, the final moments now approach rapidly. The iron core grows larger. Fusion fails to maintain equilibrium. Gravity prepares to overwhelm the star completely. Soon, one of the most violent events in the universe will erupt outward from the collapsing core. A stellar explosion powerful enough to briefly outshine entire galaxies. Deep inside the core of a massive star, gravity finally overcomes the forces that once held the star stable. Fusion can no longer provide enough outward pressure to resist collapse. The iron core grows too massive. In less than a second, the core collapses inward catastrophically. The speed of this collapse is difficult to imagine. Matter falls inward at enormous velocities. The core compresses more and more tightly. Temperatures rise into the billions of degrees Celsius. Electrons and protons are forced together under immense pressure. They combine to form neutrons and neutrinos. The core rapidly transforms into an incredibly dense, neutron-rich object. At first, the collapse continues unchecked. Gravity crushes the inner core inward, relentlessly. But eventually, the matter becomes so compressed that neutron degeneracy pressure suddenly resists further collapse. The inner core stiffens abruptly. The outer layers, still falling inward at tremendous speeds, slam into this suddenly resistant core. A powerful shockwave forms. the shockwave begins racing outward through the star. This is the beginning of a supernova explosion. For a brief period, the exploding star may shine brighter than an entire galaxy containing billions of ordinary stars. Supernovae are among the most energetic events in the observable universe. In only seconds, enormous amounts of energy are released outward into space. The explosion tears apart the outer layers of the star completely. The brightness of a nearby supernova can become visible even during daytime on planets many light-years away. Ancient human civilizations occasionally recorded mysterious new stars appearing temporarily in the sky. Some of those observations were actually supernova explosions inside the Milky Way galaxy. One famous example occurred in the year 1054. Astronomers in several parts of the world documented a bright new object, visible even during daylight for weeks. Today, the expanding remnant of that explosion is known as the Crab Nebula. Supernovae do more than destroy stars. They also create many of the heaviest elements in nature. During the explosion, temperatures and pressures become so extreme that atomic nuclei rapidly capture particles and undergo complex nuclear reactions. Elements heavier than iron form during these violent moments: gold, uranium, many rare heavy elements found on Earth. These materials are then blasted outward across interstellar space. In this way, supernovae enrich galaxies chemically. Future stars and planets form partly from the remnants of earlier stellar explosions. The atoms inside human bodies contain material forged during ancient supernovae long before Earth existed. Every breath of oxygen, every atom of calcium in bones, every trace of iron in blood, all ultimately originated through stellar processes across cosmic history. Supernova explosions also influence the structure of galaxies themselves. The expanding shockwaves compress nearby gas clouds. In some regions, this compression may trigger the formation of new stars. Destruction and creation become connected processes in galactic evolution. The explosion spreads material outward at thousands of kilometers per second. Huge expanding shells of gas race into surrounding space. Over thousands of years, these remnants continue growing larger and more diffuse. Telescopes observe beautiful supernova remnants throughout the galaxy. Delicate glowing filaments, expanding bubbles of ionized gas, twisting magnetic structures. These remnants preserve traces of the original explosion long after the star itself vanished. Yet the central core does not always disappear entirely. What remains behind depends mainly on the mass of the collapsing core. Some explosions leave behind neutron stars. Others collapse further into black holes. A neutron star is extraordinarily dense. Imagine compressing more mass than the Sun into a sphere only about 20 kilometers wide. The density becomes almost beyond ordinary intuition. Matter inside neutron stars behaves in ways still not fully understood by physics. Neutrons become packed together extremely tightly. Conditions may approach those found inside atomic nuclei themselves. The exact internal structure remains an active area of scientific research. Neutron stars rotate very rapidly after formation. Conservation of angular momentum causes the collapsing core to spin faster as it shrinks. similar to how an ice skater spins faster by pulling their arms inward. Some neutron stars rotate many times per second. Their magnetic fields can become incredibly strong. Beams of radiation may emerge from their magnetic poles. If these beams sweep across Earth repeatedly, astronomers observe regular pulses of radiation. Such objects are called pulsars. Pulsars function almost like cosmic lighthouses rotating through space. The pulses can be astonishingly precise. Some pulsars rival atomic clocks in regularity. Tiny variations in their timing help astronomers study gravity, magnetic fields, and even the structure of space-time itself. Other collapsing cores become even more extreme. If the remaining mass exceeds certain limits, neutron degeneracy pressure cannot stop collapse entirely. Gravity continues compressing matter inward. Eventually, a black hole forms. A region where gravity becomes so strong that not even light can escape once it passes beyond a boundary called the event horizon. Black holes are not empty holes in space in the ordinary sense. They are regions where matter has collapsed into extraordinary density. Their gravity strongly warps space-time itself, according to Einstein's theory of general relativity. Massive stars therefore experience some of the most dramatic endings in nature. Quiet stellar balance gives way to violent collapse. Stable fusion suddenly fails. Entire stars explode outward into space. Yet these endings also enable new beginnings across the universe. Without supernovae, galaxies would contain far fewer heavy elements. Rocky planets like Earth would be difficult or impossible to form. Complex chemistry would remain limited. In many ways, supernovae help make biological life possible. Even today, astronomers continue monitoring massive stars that may eventually explode. Betelgeuse, for example, will likely become a supernova someday, but probably not within any near-human time frame. When massive stars explode, the effects can remain visible for thousands or millions of years afterward. Expanding remnants drift through space slowly. Radiation continues streaming outward. Newly formed neutron stars or black holes remain behind as silent evidence of the collapse. Supernovae also release enormous numbers of neutrinos, tiny, nearly massless particles that interact only weakly with matter. During a supernova, most of the explosion's energy may actually leave in the form of neutrinos rather than visible light. Trillions of neutrinos pass through Earth every second, even now. During a nearby supernova, vast additional numbers would stream through planets almost effortlessly. Detecting neutrinos from supernovae helps scientists study the internal processes of stellar collapse directly. Although supernovae appear sudden from a cosmic perspective, they are the result of millions of years of stellar evolution leading gradually toward instability. The brightness of the explosion lasts only a short time compared to the star's overall lifespan, yet its consequences spread across entire regions of space. Matter, radiation, shock waves, and compact remnants all remain after the explosion fades. From those remnants, future clouds may eventually form new stars once again. The cycle of stellar evolution continues across the galaxy. Birth, stability, transformation, collapse. And from the ashes of dead stars, new generations slowly emerge. After a supernova explosion fades, the remains of the star continue drifting through space. Expanding gas clouds spread outward slowly across light years. Heavy elements forged inside the star mix into the surrounding galaxy. The death of one star becomes part of the beginning of future systems. Stellar evolution is not an isolated process. Stars constantly influence one another through gravity, radiation, stellar winds, and the recycling of matter. Entire galaxies evolve partly because generations of stars are born, age, and die over cosmic time. The early universe looked very different from the universe humans observe today. Shortly after the Big Bang, the cosmos contained mostly hydrogen and helium. Very few heavier elements existed at all. The first stars formed from these simple ingredients. Astronomers sometimes call them population 3 stars. These stars were likely very massive and lived short lives. Because the early universe lacked many heavier elements, cooling processes inside primordial gas clouds worked differently from those in modern galaxies. This may have favored the formation of especially massive stars during the universe's earliest eras. Those first stars likely transformed the cosmos profoundly. Through fusion and supernova explosions, they produced the first significant amounts of heavier elements: carbon, oxygen, silicon, iron. The raw materials required for rocky planets and complex chemistry gradually accumulated. Later generations of stars formed from increasingly enriched clouds of gas and dust. Each generation inherited material processed by earlier stars. In this way, galaxies slowly became chemically richer over billions of years. Our Sun is not a first-generation star. It formed from matter already enriched by many earlier stellar life cycles. The solar system contains heavy elements because older stars lived and died long before Earth formed. In astronomy, elements heavier than helium are often called metals, even when they are not metals in the ordinary chemical sense. Oxygen and carbon, for example, are included in this broader astronomical definition. Younger stars forming today generally contain higher metallicity than the earliest stars. This chemical enrichment influences planetary formation as well. Rocky planets require heavy elements. Without earlier generations of stars creating those elements, Earth-like worlds would be difficult to form. The existence of solid surfaces, oceans, atmospheres, and biology depends deeply on stellar history. In many ways, planets are secondary products of stellar evolution. Stars form first. Their surrounding disks create planets later, and future stars recycle the material left behind from earlier systems. The universe operates through long chains of transformation. Galaxies themselves are enormous collections of these interconnected cycles. The Milky Way contains hundreds of billions of stars. Some are newly forming inside molecular clouds. Others are stable main sequence stars. Some are white dwarfs cooling quietly. Others are neutron stars, or black holes left behind after supernovae. Different stellar ages coexist throughout the galaxy simultaneously. Spiral galaxies, like the Milky Way, often contain active star-forming regions inside their spiral arms. Gas clouds become compressed there more easily. New stars emerge gradually from dense molecular clouds. Bright young blue stars frequently illuminate these regions. Elliptical galaxies differ in appearance and activity. Many contain older stellar populations and relatively little new star formation. Their brightest eras of stellar birth may have occurred billions of years ago already. Galaxies, therefore, evolve much like ecosystems on enormous scales. Star formation rates rise and fall over time. Gas reserves become depleted or replenished. Stellar populations gradually age. Cosmic structures change slowly across billions of years. Supernova explosions contribute strongly to this galactic evolution. Their shock waves compress nearby clouds. Their radiation heats surrounding gas. Their heavy elements alter the chemistry of future star systems. The death of stars shapes the birth of later generations. Some regions of galaxies become stellar nurseries filled with glowing nebulae and young stars. Other regions contain ancient globular clusters populated mostly by very old stars. These globular clusters are among the oldest structures in many galaxies. Their stars formed early in cosmic history and often contain relatively low metallicity because fewer earlier stars existed to enrich the gas at that time. By studying stellar compositions, astronomers can reconstruct parts of galactic history. Chemistry becomes a kind of cosmic memory. Even the position of stars inside galaxies can influence their evolution. Dense central regions contain more stellar interactions and stronger gravitational effects. Outer regions may remain quieter and less crowded. Environment matters throughout cosmic evolution. Binary star systems also play important roles. Many stars exist not alone but paired with companions orbiting one another. These systems can exchange matter in complicated ways as stars evolve. Some white dwarfs gain matter from companions and eventually explode as type Ia supernovae. Some neutron stars pull gas from nearby stars and emit powerful X-rays. Binary interactions create many fascinating astronomical phenomena. The Milky Way itself continues evolving even now. New stars still form inside molecular clouds. Old stars continue dying. Black holes and neutron stars drift silently through the galaxy. The stellar cycle remains active. Yet galaxies also change through interactions with other galaxies. Gravity slowly pulls neighboring galaxies together over immense periods. The Milky Way and the Andromeda Galaxy are expected to collide billions of years in the future. Such galactic mergers dramatically reshape stellar populations and trigger bursts of new star formation. Entire galaxies can merge gradually into larger structures. Even on these enormous scales, stellar life cycles remain central to the process. Throughout the observable universe, countless stars are currently forming and dying simultaneously. Some stars visible tonight may already no longer exist because their light began traveling toward Earth long ago. Astronomy often reveals the past rather than the present. Light itself requires time to cross space. Observing distant stars means observing earlier moments in cosmic history. The farther humans look into space, the farther back in time they also look. Modern telescopes allow astronomers to study galaxies billions of light-years away. These observations help scientists understand how stellar evolution changed across different eras of the universe. Younger galaxies often appear more active and irregular than nearby mature galaxies. Yet despite all this immense diversity, the same basic physical laws apply everywhere. Gravity shapes clouds into stars. Fusion powers stellar cores. Heavier elements form gradually through nuclear reactions. And stellar remnants continue influencing the cosmos long after stars themselves die. The life cycle of stars, therefore, becomes part of the larger evolution of galaxies and of the universe itself. Humans exist within this ongoing cosmic process. Earth formed from recycled stellar material. The Sun belongs to a later generation of stars enriched by countless earlier deaths and rebirths. Even the atoms inside living organisms carry traces of ancient stellar history. The night sky may appear calm and unchanging at first glance. But behind that quiet appearance, galaxies continuously transform through slow cycles of creation and destruction unfolding across billions of years. And far into the future, the universe itself will continue changing long after the stars visible today have faded away. Far into the future, the universe will look very different from the one humans see today. The bright stars visible in the night sky are temporary features of cosmic history. Even galaxies themselves continue changing slowly across unimaginable spans of time. Stellar evolution does not end with individual stars. The long-term future of the cosmos is shaped by the gradual aging and disappearance of stellar populations everywhere. At present, the universe is still relatively active. New stars continue forming inside galaxies. Molecular clouds still contain large reserves of hydrogen gas. Fusion continues illuminating billions upon billions of stars across space. But this activity cannot continue forever. Star formation slowly consumes the available gas supply inside galaxies. Some gas is recycled through stellar deaths and supernovae. Yet over extremely long timescales, usable star-forming material gradually becomes less abundant. The universe slowly ages. Astronomers sometimes divide the future universe into broad eras based on the dominant types of objects present. The current age is often called the stelliferous era, the era of stars. During this period, stars remain the primary visible sources of energy and structure throughout galaxies. This era began after the first stars formed in the early universe and will continue for trillions of years into the future. Even after stars like the Sun disappear, many small red dwarf stars will continue shining. Red dwarfs burn fuel extremely slowly and efficiently. Their lifetimes may extend into the trillions of years. Some of the final ordinary stars in existence may be dim red dwarfs glowing faintly in an aging universe. Over time, however, even red dwarfs will exhaust their fuel eventually. Star formation rates will continue declining. Galaxies will become darker and quieter. The brilliant blue stars common in young galaxies today will vanish first because they live such short lives. Gradually, stellar populations will shift toward smaller and dimmer remnants. White dwarfs, neutron stars, black holes. The cosmos will slowly fill with the remains of ancient stars. White dwarfs themselves continue cooling across immense spans of time. Eventually, after trillions of years, they may cool enough to become black dwarfs. Cold, dark stellar remnants no longer emitting significant visible light. No black dwarfs exist yet because the universe is still far too young. But in the distant future, they may become common throughout galaxies. Ancient stellar embers drifting silently through darkness. Neutron stars and black holes may survive even longer. Some neutron stars gradually cool and become increasingly difficult to detect. Black holes, meanwhile, persist for extraordinary lengths of time. According to current physics, black holes slowly lose energy through a process called Hawking radiation. This process is extremely gradual for large black holes. A stellar mass black hole may require vastly longer than the current age of the universe to evaporate completely. Supermassive black holes at galactic centers could survive for unimaginable spans of time. Galaxies themselves will also continue evolving. The Milky Way and Andromeda are expected to merge billions of years from now. Their stars will mostly pass one another without direct collisions because the distances between stars are enormous. Yet the shapes of the galaxies will change dramatically. Gas clouds will interact. New waves of star formation may briefly occur. Eventually, the merged system may settle into a large elliptical galaxy. Over still longer timescales, many galaxies beyond the local group will disappear from view entirely. The expansion of the universe continues, carrying distant galaxies farther away. Space itself expands between large cosmic structures. As expansion continues, distant galaxies recede faster and faster. In the far future, observers inside our local galactic group may no longer see evidence of most other galaxies at all. The observable universe will appear emptier than it does today. Much of the broader cosmos will slip permanently beyond observational reach. During these distant eras, stellar remnants may occasionally interact gravitationally. Black holes may capture nearby objects. White dwarfs may collide in rare events. Neutron stars may merge and release bursts of gravitational waves and heavy elements. But such events become increasingly rare as galaxies age and disperse. Eventually, the universe may enter what some physicists call the degenerate era. Ordinary star formation largely ceases. Stellar remnants dominate the cosmos. The bright, active universe familiar today fades into a darker and quieter state. Beyond this lies even deeper uncertainty. The very long-term future of matter itself remains an open question in physics. Some theories suggest protons may eventually decay over extraordinarily long timescales, though this has not been experimentally observed yet. If proton decay occurs, even ordinary matter may slowly disintegrate in the distant future. White dwarfs, planets, gas clouds. Much of the familiar material structure of the universe would gradually disappear. Black holes may then become some of the last surviving large structures. Yet even black holes slowly evaporate through Hawking radiation, according to current theory. Given enough time, perhaps even they eventually vanish. These timescales stretch far beyond ordinary human intuition. Trillions, quadrillions. Numbers so immense they become difficult to truly imagine emotionally. Human civilization occupies only a tiny instant within cosmic history. And yet, despite the enormous scale of these ideas, the same physical laws govern both stars and humans alike. Gravity shapes galaxies. Nuclear fusion powers stars. Atoms forged in ancient supernovae later become part of planets and living organisms. The universe remains deeply interconnected across time. The carbon inside living cells once formed inside stellar cores. The oxygen humans breathe emerged from nuclear fusion long before Earth existed. Even calcium, iron, and phosphorus originated through earlier generations of stars. Human bodies carry the chemical memory of ancient stellar evolution. Looking at the night sky, therefore, also means looking at a vast, ongoing cycle of transformation. Clouds become stars. Stars create heavier elements. Stars die and return matter to space. New systems form from those remnants. The cycle continues across galaxies for billions and trillions of years. Even the eventual fading of stars does not erase the importance of their existence. For much of cosmic history, stars create structure, chemistry, light, and complexity throughout the universe. They transform simple hydrogen and helium into the rich diversity of matter observed today. And although the distant future may become dark and quiet, the present universe remains full of active stellar life. New stars continue forming tonight somewhere inside distant molecular clouds. Other stars are quietly cooling. Some massive stars may already be nearing collapse. The great cycle continues constantly across the cosmos. From fragile clouds of gas to dense stellar remnants, the life cycle of stars shapes nearly every visible structure in the universe. And through those stars, the universe slowly learns to build complexity from simplicity across the vast silence of space. For most of human history, stars appeared permanent. Ancient people looked upward and saw lights that seemed fixed and eternal. The night sky changed slowly enough that entire civilizations could pass without noticing major differences. Yet modern astronomy revealed something far deeper. Stars are not eternal points of light. They are physical objects with beginnings, transformations, and endings. Each star follows a long evolutionary path shaped mainly by mass and gravity. The story begins inside cold molecular clouds drifting through galaxies. Gravity slowly gathers gas together. Dense regions collapse inward. Protostars emerge. Eventually, nuclear fusion ignites in stellar cores. A star is born. For long periods, stars remain relatively stable. Gravity pulls inward constantly. Fusion pushes outward. These opposing forces maintain a delicate balance, lasting millions, billions, or even trillions of years, depending on the star's mass. Small stars burn slowly and quietly. Massive stars burn rapidly and intensely. The brightest stars often live the shortest lives. The dimmest stars may outlast almost everything else in the universe. Over time, stellar cores gradually change composition. Hydrogen becomes helium. Helium may become carbon and oxygen. In massive stars, fusion continues toward heavier elements. Stellar evolution is ultimately a long process of nuclear transformation. As stars age, their structures shift. Some expand into red giants or red supergiants. Outer layers drift outward into space. Internal fusion shells become more complex. The calm appearance of stars hides constant internal change. The final stages depend strongly on mass. Sun-like stars shed their outer layers gently and become white dwarfs. Massive stars collapse violently and explode as supernovae. Some leave behind neutron stars. Others form black holes. Yet regardless of the specific ending, stars continuously return material back into the galaxy. The matter created during stellar evolution does not disappear. It becomes part of future generations of stars and planets. Cosmic recycling never truly stops. The universe today contains chemical richness because countless earlier stars lived and died before the solar system formed. Carbon, oxygen, silicon, iron. Nearly every heavy element essential to Earth originated inside ancient stars. Human beings are therefore connected to stellar evolution in a very literal sense. The atoms inside living organisms once traveled through earlier generations of stars long before Earth existed. The life cycle of stars became part of the life cycle of planets and eventually biology itself. Modern astronomy allows humans to study these processes across enormous distances and timescales. Telescopes observe newborn stars hidden inside dusty nebulae. Other instruments detect white dwarfs cooling quietly through deep time. Some telescopes capture the expanding remnants of ancient supernova explosions. The sky preserves many stages of stellar evolution simultaneously. Looking outward into space also means looking backward in time. Light from distant stars requires years, centuries, or millions of years to reach Earth. Some stars visible tonight may already have changed or disappeared entirely since their light first began traveling toward us. Astronomy reveals a universe always in motion, even when it appears calm. The scale of stellar evolution can feel difficult to imagine fully. Human lives last decades. Civilizations last centuries or millennia. Stars often evolve across billions of years. Cosmic time stretches far beyond ordinary human experience. Yet despite those immense scales, the physical principles involved remain understandable. Gravity compresses matter. Pressure resists collapse. Fusion releases energy. Mass determines how evolution proceeds. The same laws apply throughout the observable universe. This universality gives astronomy a quiet sense of continuity. The stars visible above Earth obey the same physics as stars inside distant galaxies billions of light-years away. Across enormous separations of space and time, the cosmos remains connected through shared physical laws. The future universe will continue changing long after the stars visible today fade away. Red dwarfs may glow for trillions of years. White dwarfs will cool slowly into darkness. Black holes may persist for unimaginable spans of time. The cosmos itself evolves continuously. But during this present era, the universe remains rich with active stellar life. Somewhere tonight, stars are forming inside cold clouds. Somewhere else, giant stars are nearing collapse. Across distant galaxies, supernovae are scattering newly forged elements into space at this very moment. The cycle continues quietly across the universe. From the perspective of Earth, the stars may seem silent. Yet every point of light overhead represents a vast physical story unfolding across time. Some stars are young. Some are ancient. Some may already no longer exist except through the light still traveling toward Earth. The night sky becomes deeper and more complex the more carefully it is understood. And perhaps one of the most remarkable aspects of stellar evolution is how ordinary its ingredients truly are. Simple hydrogen gas, gravity, time. From these simple beginnings emerge stars, planets, chemistry, galaxies, and eventually living observers capable of studying the universe itself. The life cycle of stars is therefore not only a story about distant objects in space. It is also part of the larger story of how complexity develops across the cosmos, how matter changes form, how energy flows through the universe, and how the elements necessary for worlds like Earth gradually came to exist. Long after this moment passes, the stars will continue evolving according to the same quiet physical laws. Clouds will collapse. Fusion will ignite. Giants will expand. Supernovae will erupt. Stellar remnants will cool through darkness. The cycle will continue across the cosmos for ages beyond human imagination. And beneath the calm appearance of the night sky, that immense process is unfolding even now.